Okay, 11.6 is the last section in chapter 11. And we're going to be talking about exponential and logarithmic equations. So we're taking everything we've learned in chapter 11 and we're combining it all now and using what we're learning into solving these equations. I have 4 different properties here of exponential and logarithmic equations. And we're familiar with 1 and 2. And actually more 2, but it's the same with 1. If x equals y, then we can say that b of x, b to the x power equals b to the y power. Although we're more familiar with 2, which says that b to the x equals b to the y. And if we have the same basis, then we can say that they're exponents, or x equals y. So 1 and 2 are just the reverse of each other. And so are 3 and 4. 3 states if x equals y, then we can say the log of x equals the log of y. And then on 4, it says if they're telling us that the log of x equals the log of y, then we can say that x equals y. So let's look at some different examples and using those properties. Example number 1 is 3 to the x power equals 12. Now, in this chapter so far, whenever we've had a variable in the exponent, in order to solve it, we've always had to get the same base. And then we would set the base, then once we had the same base, we would just set the exponents equal to each other. But what if we can't get the same base? For instance, I cannot put 12 with a base of 3. It doesn't work that way. So we are going to use that property number 3. That's right above. And we're going to use our common log, which remember that's the base 10. We don't have to write a base on it. And this is also what we can use in our calculator. So if you cannot get the same base, I am going to use number 3. Number 3 says if x equals y. Well, here's my x, and that's going to equal to my y. Then I could say the log of x equals the log of y. So I can take the log of both sides. And it will work. So, if I cannot get the same base, I go ahead and take the log of both sides. Then I'm going to use my power rule. Because my x is an exponent and I don't want an exponent, I can bring that x down. Remember the exponents go to the front. So now I have x times the log of 3 equals the log of 12. Well, how am I going to solve for x? I'm just going to divide both sides by the log of 3. So x equals the log of 12 divided by the log of 3. Now, when you put this in your calculator, it needs to be the log of 12. You need to either end your parentheses, close it off with parentheses, or put equals after that, and then divide it by log of 3. Okay, otherwise you're not going to have the right answer. So, when you put that in your calculator, your x is going to be approximately if I round to 3 decimal places, 2.262. And that is my solution. Now, checking it. What that is saying is 3 to the 2.262 power is going to equal to 12. But because I had to round, it's not going to be exactly 12. But I think if you put that in your calculator, I think you get like 12.00 and then your numbers starting up. So it is pretty close, and that's just because we rounded. If you didn't have to round, then you would have the exact number. So I could not get the same base. So I took the log of both sides and then solved for that variable. Look at example number 2. Again, I have e raised to the 0.003x equals 40. I cannot put 40 with the same base of e. Okay, so I'm going to use that property number 3 rule. So I'm going to take the log of both sides. Now, whenever we have an e in our equation, we will always use the natural log. Because remember what natural log is? It's log base e. Okay, so you always use a natural log when we're dealing with e. So if I take the natural log of e to the 0.003x power equals the natural log of 40. Go ahead and use your power rule. We're going to take that exponent, move it down to the front. The nice thing about using the natural log with this e, remember the natural log of e is going to equal to 1 because the log base e of e equals 1. So this whole thing right here is just 1. So 1 times 0.003x is just that 0.003x. And that equals to the natural log of 40. So I'm still solving for x. And I divide both sides with 0.003. And x is going to equal to the natural log of 40 divided by 0.003. And when you put that in your calculator, you should get 1,229.626 if you round to 3 decimal places. Okay, 1,229.626. Hopefully you're trying these out on your calculator, seeing if you're getting the same answers, because you need to know how your calculator is working. And remember, you make sure you're putting the right parentheses or equal signs or whatever and getting the correct answers. So the second thing we're going to talk about is if we have, well, actually here again, we have one log and it's a little bit more extensive. I want you to solve, but give it to me an exact solution, meaning if it has a fraction, you keep it as a fraction. I don't want a decimal that you've rounded. If it has a radical in it, you keep it as a radical, because otherwise you're going to have to round, and don't round. Exact solutions means do not round. Don't put it as a decimal and you decide you want to round wherever you want to round to. So this has one log. All the other problems, when we've had one log on one side, we will just write it in exponential form. When I write this in exponential form, it is 2 to the 4th power equals the x plus 5 quantity cubed. So, now I have it in exponential form. All I need to do now is solve for x. Well, when I'm raising something to the 3rd power, especially that x to the 3rd power, I want just one x. If I'm raising it to the 3rd power, how can I get rid of that cubed? Remember, we would have to cube root it. So when I cube root the right hand side, I have to cube root the left hand side. And when I take the cubed root of 2 to the 4th power, I want a group of 3, okay? So I want to have 2 on the outside, that's one group of 3, times the cubed root of 2, there's 2 left over inside. And when I take the cubed root of something that's being cubed, I am just left with the x plus 5. Okay, now I'm still solving for x. To solve for it, I just need to subtract 5 from both sides. Remember, I've said this before. If you are subtracting from something in a radical, you need to do it in the front. Or if we're adding something, you need to put it in the front. Don't put it behind it, because I'm not going to know if you don't write your radicals right or whatever. Is it underneath the radical or what? So make sure you put it into the front. So now I'm going to subtract 5, so I have a negative 5 plus 2 times the cubed root of 2 equals my x. So that looks very ominous. Let's go ahead and just check it. If we check it and see how that goes into our solution, into our equation, if I have log base 2 of my x is a negative 5 plus 2 times the cubed root of 2, that's all x. And look, and we have plus 5. So here's my x plus 5. Okay, and that needs to be cubed and equal to 4. Well, inside my parentheses, I do have some things I can take care of. My negative 5 and plus 5 can be canceled out. So I am left with log base 2 of 2 times the cubed root of 2 cubed equals 4. So go ahead and let's cube what's underneath in the parentheses. 2 cubed is 8. The cubed root of 2 cubed is just times 2. It's just what's underneath that radical. And that's going to equal to 4. So I have the log base 2 of 16 equals 4. Well, I can put this in exponential form and say 2 to the 4th power equals 16. Well, 2 to the 4th power is 16, so they do equal, and it does check. So you can check your solutions to make sure you have been doing them correctly. So my solution set would be a negative 5 plus 2 times the cubed root of 2. And that's my answer. For example number 4, I have 3 logs. Everything so far, if I have one log, I put it in exponential form. If I have a log on both sides, I can use that property 4. Kind of like same base, but now I need the same log. But first of all, I need to make the left-hand side a little concise. So if I use my quotient rule, because I just want one log on each side, not 2 on one and 1 on the other. If I use my quotient rule, I have the log base 2 of my numerator over my denominator. That's what that minus sign means. Okay, and that's going to equal to the log base 2 of 7. Now I have the log on each side. We're going to use that property number 4, which states if we're taking the log of x, and that's equal to the log of y, then x is going to equal to y. So here's my x and here's my y, and I can set them equal to each other. So I have x plus 1 over x equals 7. Now I just need to solve for x. So in order to solve for x, multiply both sides by x. I have x plus 1 equals 7x. Subtract x, 1 equals 6x. Divide by 6, and I have 1/6. So my solution is 1/6. If I plug in that 1/6 up in here, I still have a positive log. If I put my 1/6 here, I still have a positive log, so that still works. Okay? Now, look at example number 5. I have 2 logs, but do I have 2 logs on either side of the equation, of the equal sign here? No, I don't. I only have logs on the one side. I can go ahead and use my product rule to simplify the left-hand side of my equation. Remember, the product rule means I'm going to multiply my two logs that I've added, and that's going to equal to 2. When I have one log, I put it in exponential form. So, what's the base here of my log? It's understood to be 10. It's that common log. So, that base raised to the 2 power is going to equal to this x that's right here. So x times x minus 21. So let's go ahead and simplify what we have. We have 10 squared equals x squared minus 21x. What kind of equation do I have? I see that x squared. I have a quadratic, so we're going to put it in standard form so we can solve a quadratic equation. Maybe we can factor it. If we can factor it, that would be the easiest. Otherwise, we also can use the quadratic formula. So subtract 10 from both sides. I have 0 equals x squared minus 21x minus 100. Everybody see that? All I did was put my quadratic in standard form. Can I factor this quadratic equation? Yes, I can. Makes it a lot easier. I have x minus 25 and x plus 4. Whenever we have a quadratic and we can factor it, how do I solve for the x? Set those factors equal to 0. So x equals 25 and x equals negative 4. Now, let's see, can we use them both or can we just use one? If I put them into my x, the 25 works, they both remain positive when I put them in for x. But when I put negative 4, I have a negative log here. In the first one, I actually have a negative log in the second one. It doesn't matter if it's one or both. If one of them is a negative, then we can't use that number. So I'm not allowed to use a negative 4, and so therefore my solution set is just 25. So make sure you check to see if it makes it have a negative log. If you have one log, put it in exponential form and solve. When you have two logs, when you have logs on both sides, you can use that property 4 and set what we're taking the log of equal to each other. Looking at the last thing we're going to talk about, and this is a compound interest formula. Okay, the compound interest formula. I have the formula written right here. A is how much is in the account once we've had all this interest paid to it. Okay, P is your principal amount. It's the amount of money we're starting with. It's the principal amount. R is your rate as a decimal. Make sure you change it to a decimal. N is the number of times you're paid in a year. So, if you are paid annually, how many times are you paid? Just one time. If you are paid semi-annually, how many times are you paid? You are paid twice. These are numbers for N. If you are paid quarterly, you are paid 4 times a year. And if you are paid monthly, you are paid 12 times a year. So these numbers here are numbers that can go in for N. It depends upon what the problem says and how many times you are paid in 1 year. And then of course T is just the number of years that we're talking about. Example number 6 states this. How much money will there be in an account at the end of 5 years if $1,000 is deposited at 6% compounded quarterly? So let's look at, we are looking for A equals P is your principal amount. How much money are we starting with? We're starting with that $1,000. So 1 plus my rate is 6%. I need it in a decimal, so I have 0.06. Remember, move it over 2 places to the left and put your decimal place there. And it says it's compounded quarterly. That means it is going to be compounded 4 times within the year. And then I'm raising this whole thing to 4 times in a number of 5 years. So 4 times 5. So let's go ahead and try to work this problem out, making sure you put it in your calculator correctly and everything. So we have our 1,000. In the parentheses, I would put the 0.06 divided by 4 equals, and then plus the 1 to it. Okay. Now you can do it other ways if you continue using all these parentheses. Just make sure you know how to use your calculator correctly. If you want to do it that way and you can get it the right answer, then that's just fine. So I'm giving you the answer in your notes. Make sure you can put it in your calculator so you can get the correct answer. So inside your parentheses, you should come out with 1.015, and that's going to be raised to the 20th power. That 4 times 5 is the 20th power. So when you take that 1.015, raise it to the 20th power, multiply that by 1,000, the amount in your account after 5 years and with 6% interest, and it's compounded quarterly, the amount in your account will be $1,346.86. That is the total amount of money that will be in your account after those 5 years. Now, pay very close attention to what they are asking you for. Here they're asking how much money will be in the account. Okay, that is your A. But what if they asked you how much interest will be earned in 5 years? Okay, what if they ask you how much interest will be earned in the 5 years? So how would you find that? You still have to solve for your A, but in order to find the interest, you're going to take what you have now, the $1,346.86, subtract what you started with, subtract your principal amount, and the interest earned is going to be the $346.86. That is how much money you added to your account in the 5 years. So pay very close attention to what they are asking you. You're going to get in such a habit of always finding A, and then all of a sudden the question is going to come up and ask you for how much interest, not how much is in the account. So pay very close attention to that. Well, that is the end of chapter 11.